Hello there, this is Ms. Nakayama, and today's lesson is 11.2, Finding Limits Using Properties of Limits. So, in this video, we are going to cover finding limits of constant functions and the identity function. We're going to find limits using properties of limits. We're going to find one-sided limits, and we're going to find limits of fractional expressions in which the denominator is 0. Because I know you know by now that we cannot have zero in the denominator. So first and foremost, there is one central theme to most of these problems, or really all of these problems, and that is you're going to plug numbers in and evaluate. But look at the first one here. The limit of a constant function. The limit of a constant function is that constant. The limit of f of x as x approaches a is equal to, if f of x is equal to c. As I just said, the limit of the function, the limit of any constant is that constant. So when I say plug it in, y'all, if it looks like this, if you plug in a into c, well, there's no value to plug in for x. So that's why your answer is just c. So these two examples, find the following limits. What is the limit of 11 as x approaches 8? Well, there's no x in there for me to put 8 in for x. So my limit, that is a constant function, and the limit is just 11. The limit as x approaches 0 of -9. Again, no x for you to plug 0 in for x. So my answer is just -9. That's simple. All right. Now we have the identity function. The identity function is f of x equals x. So the limit of any function, the limit of x as x approaches a number, is that number. Okay, that's what that says. So if I plug in a for x, I'm going to get a. In words, the limit of x as x approaches any number is that number. So again, central theme, plug in for x. So the limit of x as x approaches 19 is 19. The limit of x as x approaches the negative square root of 2 is the negative square root of 2. Again, that's simple. Okay? The limit of a sum. Okay? So the limit of a sum is the sum of the limits. If you want all the words, there are the words. So all you're going to do, again, is plug in a for x. Here's our example. Okay? The limit of the sum, x plus 16, as x approaches -3. That means I'm going to go plug in -3 for x. And when I do, I have 13 because I didn't write the negatives. -3 plus 16 is 13. Okay? The limit of a difference is the difference of the limits. Again, plugging in. Okay? I'm going to plug in 14 for x. What is 19 minus 14? 5. So the limit is 5. The limit of a product is the product of the limits. I'm going to plug in for x, and then I'm going to multiply those two limits. So what's the limit of -10x as x approaches 7? I'm going to plug in 7 for x, and -10 times 7 is -70. So that's my limit. Okay? The limit of a monomial. So basically you need to be familiar with all these different functions you're seeing. Okay? The limit of a monomial is just going to be that monomial evaluated at x equal to a. Same thing. Okay? The limit of -7x cubed as x approaches 2. I'm going to plug in 2 for x. That's going to be -7 times 2 cubed. 2 cubed is 8, so it's going to give me -56. All right. A polynomial. Again, the limit of a polynomial is equal to the value of that polynomial at a. So what do you get when you plug in a every time you see x in the polynomial? So what's really important is to actually recognize that you have this polynomial. Actually, that's coming up next. All right, so if I go plug in 2 every time I see x, all right, I put it in parentheses. Remember, what's most important is if you ever plug in a negative number, you need to put parentheses around it, because now I can just put it in my calculator like that and get my answer of positive 61. Okay, the limit of a power is the power of that limit. That's exactly what's happening. Same kind of thing. So example 8, what am I going to do? I'm going to plug in 4 into x, and 3 times 4, remember your order of operations, 12 minus 5 is 7, and 7 cubed is 343. All right, the limit of a root is the root of a limit. Again, in words if you prefer that. So example 9, again, I'm going to plug in -1 in for x, and here's an example where it is most important to put parentheses around that. Even though I say this over and over again, y'all, there's always somebody who doesn't do it and gets it wrong. -1 squared is +1, and so 6 minus 4 is 2, so the answer is just the square root of 2. All right, the limit of a quotient is the quotient of the limits, but you have to be careful. The denominator cannot be 0, okay? So in example 10, again, I'm going to plug in, I hope you're getting this theme here, I'm plugging in 2 everywhere I see x. So when I plug in 2 and 2 and 2, that simplifies. Put it in your calculator in one fell swoop with that horizontal fraction bar, and that gives me an answer of -3. Okay, so here's a review of all the limits. You don't need to pause here. I went through each of them, but if you didn't write them down, just be familiar with them. That's fine. Okay, and we can use those same properties to do piecewise functions or one-sided limits. So here are one-sided limits. Okay, this says f of x is -1 if x is less than 1, and the cube root of 2x minus 1 if x is greater than or equal to 1, and that's just a period for the end of the sentence. Anyway, the limit of f of x as x approaches 1 from the left. So 1 from the left of 1 are those numbers that are less than 1. That means I'm going to use that function and plug 1 into that function. Well, that's a constant function because there's no x. So that limit is just -1. Now, when I go down to this second one, and it says, find the limit of f of x as x approaches 1 from the right, that means those numbers are greater than 1. So I'm going to use the bottom function, and when I plug in 1, 2 times 1 is 2, minus 1 is 1, and the cube root, I put that in here, sorry, forgot. 2 times 1 is 2, minus 1 is 1, so the square root of 1 is 1. So what is the limit? Remember when we just talked about the graphing, when we looked at graphing or tables, if these two numbers are not the same, then the limit does not exist, okay? One-sided limits will always exist, but the limit as x approaches 1 doesn't exist if I have two different numbers going on here, okay? Now, the other thing we have to talk about is what happens if I plug in and I get 0 on the bottom, okay? I cannot have 0 in my denominator. So if I do, I have to think about factoring or something called rationalizing your numerator, okay? So I have 3 examples left to do this. So the first one, if you plug 1 in to this expression, I'm only worried about the bottom because I can't have 0 on the bottom. So that's 1 minus 1, which is 0, plus 3 minus 3, which is 0. So I have 0 on the bottom. And if I have 4 terms, yes, we're going back to chapter P way back in August, and we've got to factor these things. So you want to remember when you have 4 terms that we're going to factor, and we're going to group them in 2s, okay? So on this first one, when I look at those, what do they have in common? They have an x squared. And when I take out an x squared, I'm left with x minus 1. And when you look at these last 2 up top, it already says x minus 1. I actually also, to remind you that I always make sure I have that sign in between them. So the common factor between x minus 1 is just 1. So that's what I'm going to end up getting, okay? And then on the bottom, I take out a common factor of x cubed. I'm left with x minus 1. bring down my sign, which is plus. Now my common factor is 3, so I'm going to have plus 3, and what's left better be x minus 1. So how you factor that is I still have the limit as x approaches 1. My common factor is x minus 1. And what's left is x squared plus 1. Okay, this is what's left here when I take out the x minus 1. And on the bottom, again, I have x minus 1, and I'm going to be left with x cubed plus 3. So if you look at that, these two are the same factor, so I can get rid of them. And now I end up with the limit of x squared plus 1 over x squared plus 3. And now I can plug in 1. When I plug in 1 up top, I get 1, and on the bottom, I get 4. But that's not what I wrote. So let's go fix that real quick. That's supposed to be a 4. 1 over 4. Okay, so rationalizing a numerator. All right, so before we've had a radical on the bottom, and we always can't leave it like that. But if you look at this problem, the limit as h approaches 0, if I plug in 0, I've got 0 on the bottom, and I can't have that. So we do something known as rationalizing the numerator. Okay, and if you remember from before, okay, this concept again back from chapter P, a plus b times a minus b is what we use to get rid of a radical or a complex, the value of I, and that when you multiply a plus b times a minus b, you get a squared minus b squared. So I'm going to multiply, those are called conjugates, and I'm going to multiply by the conjugate of the top. Okay, this right here is my a, and this is my b. So I'm going to multiply by the square root of that plus 1 over the square root of that plus 1. Okay, so now when I multiply that, the limit as h approaches 0, I'm going to get, when I multiply the square root of 19h plus 1 times the square root of 19h plus 1, I didn't change what's under that radical. When you multiply them together, the radical goes away, leaving me with just 19h plus 1. And then it's always minus, and then 1 squared is just 1. So it's minus 1 up top, and you don't need to multiply out the bottom. Okay? Now, when I simplify this, well, I know y'all can tell me that 1 and negative 1 are going to go away. And then I'm just left with 19h up top. Well, that's an h right there and an h right there. So that actually leaves me with 19 on top, and then the square root of 19h plus 1 on the bottom. And when I plug in 0, that ends up with 19 on top, and my radical becomes the square root of 1, which is 1 plus 2, so I'm going to get 19 over 2. So, important to be able to rationalize. We've done that a lot. All right, this is the last one, and this one still have this problem of plugging in and getting 0 on the bottom if I plug in 8. Okay, so whenever you have a fraction, you always think about that. And this time, I just have to simplify my complex fraction, which again, we did way back in chapter P, okay? And the easiest way to do it is to multiply by the least common denominator, which in this case is 8x. So I'm going to multiply, and before I would write out to the side 8x over 8x, but another way to think of it is to think about multiplying every term by 8x. So 1 over x gets multiplied by 8x, 1 over 8 gets multiplied by 8x, and then x minus 8 gets multiplied by 8x. Okay? And, think about it, whenever you multiply by a fraction, this is like over 1 in these cases. So when I multiply, okay, I'm going to get, these x's are going to go away, leaving me with just 8 minus, and these 8's are going to go away, leaving me with just x. And on the bottom, again, you don't need to multiply it. It's just going to be 8x times x minus 8. Okay? Now, you do need to remember that 8 minus x is the opposite of x minus 8. Okay, we've talked about this. If you have 5 minus 2, that's equal to 3, and 2 minus 5 is equal to negative 3. So if I switch the order of my subtraction, I just have to know that I've got to have to negative 1 somewhere. So I need to think about, I have simplified my complex fraction to negative 1 over 8x. And when I plug in for 8, I'm going to get negative. I never right. Can you see that negative? You can. Anyway, there's supposed to be a negative there. When you plug in for 8, you get negative 1 over 64. So the grand theme is plug in whatever x is into the expression. And if you end up with getting 0 in the denominator, you got to try to factor or simplify that complex fraction or rationalize your numerator. Thank you so much for watching, and y'all have a great